Okay, good morning everyone. Welcome back. So yesterday we worked a lot to produce this circuit here. So this is the circuit for the quantum Fourier transform. And now today we're going to use it to compute something. But before, let us come back a little bit to the shape of this circuit. And what you can see here from a distance is that there's a kind of recursive structure in the circuit which you can see by, for instance, focusing on this block here. And you can see here that this block, in fact, corresponds to a Fourier transform on n-1 qubits, if I call n the number of qubits. So in other words, if I rewrite the same circuit in the same way, I'm going to rewrite it in a slightly different way. Like this, it's a control, then a big gate that I'm going to call U. It's a big phase gate that applies on many qubits, and it contains essentially the qubits that I'm going to circle. So all this here, I'm going to call UPH. So this is what I call UPH. And then this qubit stays unchanged. And all the rest, then you apply the block here, which I'm going to call QFT n-1. So in other words, what you see is that QFT on n qubits, which is this here, so this is QFT on n qubits, equals this circuit here. And now, and the reason why I want to point that out is that now we can try to compute the complexity of computing the QFT on the quantum computer first. So that's something I sketched yesterday. So on the quantum computer, if I count the number of gates, you see here in this first block I have of the order of n gates if you count. And then I'm going to have n of these blocks. So in total I'm going to have O(n squared gates. And now let's try to see what would be the computation we could do on the classical computer. So on the classical computer, you remember the formula for the discrete Fourier transform? There was yk 1 over square root n sum over j from 0 to big N minus 1 of exponential of 2i pi over n jk xj. So this was the formula for the discrete Fourier transform that we used. And so if you count naively the number of operations you need, it's essentially a double for loop on all the k's and then a sum on the j's. So the naive complexity of this would be big O of n big N to the cube, which if I convert it back, so remember that big N is 2 to the n, then you obtain 2 to the n squared, so 4 to the n, or let's say 2 to the n times 2 to the n. Okay, so that's the complexity of a direct discrete Fourier transform. If you do it naively, but it turns out that people have come up in the past with a better way of doing this classical. So it's still a classical way of computing it. And it's called FFT, fast Fourier transform, and I want to convince you that with this circuit I can do the FFT on the classical computer and get the scaling that people know in fast Fourier transform. And so for this, let's look at the computation we would do to simulate this circuit on a classical computer. So yesterday you did some tutorials on Qiskit and QLM and MyQLM, and you know that when you simulate a circuit on Qiskit or MyQLM, what it does, what this software do, is a classical emulation on a classical computer. But now, so let's try to do what would happen if I were to simulate a QFT circuit with MyQLM or Qiskit. So the way I would represent my wave vector psi at the beginning would be a big vector with amplitudes. And so these amplitudes I can label. So either I say it's x0, x1 until xn minus 1. That's one way of saying things. But a more convenient way would be to use a binary decomposition of the bits. So we'd have 0, 0, 0 n times. Then the second one would be x 0, 0, 0, 1, and so on and so forth until x 1, 1, 1. So that's how we represent a wave vector in a classical computer. You see, if you count, you have indeed 2 to the n components. So it's very expensive to store. And now let's see what happens if I apply a Hadamard gate on the first qubit corresponding to this wave function. So if I do h on the first so the qubit number 0, let's say number 1 on psi, then you remember what Hadamard means? So Hadamard means if my qubit is 0, I do 0 plus 1 over square root 2. And if the qubit starts with a 1, so if x1, 0, 0, 0, all the rest, so this is, then I do the x0 minus 1 over square root 2. So if you do the math, you'll find out that what you find is that you get x0, 0, 0 plus x1, 0, 0, 0 over square root 2. Same thing here, x0, 0, 1 plus x1, 0, 0, 1 over square root 2. So that's for the first part. And the second part, so meaning all the bits starting with 1, you get x0, 0, 0 minus x1, 0, 0, 0 over square root 2. And so on and so forth. So you see what's happening when you do a Hadamard gate on your wave function. The wave function you obtain is obtained by summing the half of the components with the lower half, the first half with the lower half, and here subtracting the first half with the lower half here for this part. And now if I count how much it costs me in terms of classical computations, you see I have to do 2 to the power n additions, right? So this is the price. This is the price of this Hadamard gate if I do it on a classical computer. Now, let's see what happens if I now want to do the controlled U phase times H1 times psi. Then here, this is a controlled operation. So you remember the gate of the matrix of a controlled operation was 1, 1, 1, and then the gate itself. But the gate itself, UPH, is a phase gate. And you remember a phase gate is a diagonal gate. So in principle, this should convince you that C UPH here is a diagonal matrix. So doing a matrix vector multiplication of a diagonal matrix with a vector also costs us 2 to the n. Okay? So now, in principle, I have convinced you that to reach the midpoint in the circuit here, the cost that I paid is essentially 2 to the n. Okay? I mean, 2 times 2 to the n, but it's still, in terms of big O notation, it's still 2 to the n. And that's for the first block. But now, since I'm doing a recursive algorithm, for the rest, if I count the number of total number of iterations, I'm going to repeat QFT n minus 1 is also recursive. So I'm going to do n applications of this same block. So if I count the total number of operations, so total number of operations I do is 2 to the n times n. Do you all agree with this? That I have to pay this price to do the Hadamard and the controlled, this is 2 to the n, and then I'm going to replicate this n times. Of course, it's all big O notation. I didn't work out the prefactors. Well, it turns out that this is precisely what an FFT does. So probably you know it in a different way. You know it in the big N notation. So you know that an FFT, the cost of a fast Fourier transform is n log n. And this is what this achieves. Okay? All right, so this was just a small remark on the quantum Fourier transform. And now I'm going to tell you about one of the most famous applications of quantum Fourier transforms, which is Shor's algorithm. I'm not going to do it in much detail because Pierre-Alain is going to do it better than me later this week. But I'm going to give you a brief idea of why this Fourier transform is used to factor numbers. So, as you know, the main use of a Fourier transform is to put a periodic signal to a Fourier transform and find the frequency of this signal. Oops, no, wrong. Okay. So you know that if you input a periodic signal here with a period t to a Fourier transform, what you expect to find, so if this is, for instance, time and this is frequency, then what you expect to see is a signal which is going to be peaked at 1 over t in frequency. Okay, so this is what you expect to see when you do a Fourier transform. So in the same way here, if I input a wave function psi of this form sum over x of g of x, where x here has to be understood as an integer from 0 to 2 to the n minus 1. And I know that g of x has a period, so g of x plus r equals g of x. Then what I expect to see upon quantum Fourier transform of this function is a function psi, which is sum over k of, let's say, g hat of k. And roughly speaking, I'm not going to do the full computation. G hat of k is going to have a peak here at 1 over r. Okay, so this is what I expect. And therefore, if my problem is to find the period of g, then QFT is the right function, right algorithm to use. So now, let's see why this can be used for factoring. So I'm not going to work out the full theory, but the goal of factoring is to say you have an integer number big N that you want to factor as p times q, where p and q are integer numbers. And it turns out that if you find a number a smaller than n, which is co-prime with n, so GCD of a and n is 1. So suppose you have found such a number, then if you construct the function a power x modulo n, you can construct this function. It turns out that finding the period of this function will allow you to find the factorization. I'm not going to prove it because I guess Pierre-Alain is going to explain the arithmetic behind it. But now you should believe me for now that all I have to do if I want to factor those two numbers is to find the period of this function corresponding to a to the power n modulo to the power x modulo n. Okay? And so now I want to explain to you briefly why this can be used in a Fourier transform, because now the question is, how do I produce a state? So my goal is to produce a state sum over x of f of x. So the question is, how do I produce such a state? And I'm going to require maybe not to produce f of x, but a function f tilde of x, which has same periodicity as f. I'm going to do something slightly less strict here. And for this, I'm going to argue that the following circuit works. So I start with a circuit with a couple of Hadamard gates. So here, let's call this M Hadamard gates, and then I start with a last register starting in 0. And then I'm going to suppose that I have a black box that I'm not going to focus on too much today, which does what we call modular exponentiation. And this modular exponentiation is essentially this operation. You exponentiate to the power of x modulo n. So this is what this box does. And let me give you just the definition of this box. The precise definition of this box is that if you start with x and 0 in this box, so this is modular exponentiation, then you end up with x, and here you have a x modulo n. Okay? And so here, let me also advertise the fact that this is several qubits here. In fact, the number of qubits in this line is, for a reason you can easily understand, is log 2n, because that's the number of bits I need to store a number which is modulo n, because the maximum is n. Okay? So this is not one qubit, it's several qubits. All right? So now I suppose I have such a block. Of course, there's a lot of work in this box how to do this circuit, but it's not really what I want to focus on. But nevertheless, now this is what we start with. And I want to convince you that if I do this circuit and then do a quantum Fourier transform here, then I should be able to extract the period of f, which is what I'm looking for. Okay? So let's see how it works. So first we have to work out what is the state corresponding to this stage of the circuit. And here, so you remember that h, when applied to qubit 0, is 0 plus 1 over square root 2. So if we do it for each of the qubits in this wall of Hadamard gates, we end up with a state which is going to be sum over x of x from 0 to 2 to the m minus 1. And here I'm going to forget all the 1 over square root 2 factors here. So it's proportional to, okay? Tensor 0. Okay, so that's the state I get after this wall of Hadamard gates. Now, let's look at what this box does. So what this box does is that if I have an input x, then I'm going to still have x here, but I'm going to put a power x modulo n in the register at the bottom. So let's apply this. So if I apply this rule, then I'm going to see that I have sum over x from 0 to 2 to the m minus 1 tensor, and I'm going to call it f of x. Right, this is what it is. Right, so here I work by linearity. Of course, I have a sum here, but since everything is linear, I still have a sum afterwards. Okay, and now I'm going to do a trick now. I'm going to suppose that I'm going to add a measurement here. So a measurement, you remember what a measurement means? A measurement means that I'm going to project the state corresponding to this qubit. And here I'm going to suppose that the output of the measurement is a bit string S. I'm going to suppose that the bit string that I get after the measurement is S. And we know that if we have so let's take a simple example to make it clear. So let's say I start with the state 0 plus 1 over square root 2, and someone tells me, oh, my state after measurement is 0. Then what it means is that after my measurement, the quantum register is in which state? It's in state 0, right? That's what I know. If someone tells me, oh, I get 0 as a result, it means my state after the measurement is 0. So here, if I tell you my state is S, what is the state after? The state is going to be essentially sum over x from 0 to 2m minus 1 times x times s f of x times s. So here, what I did is that, so let me tell you what I did. What I did is essentially multiply everything by identity on the first register times the projector on S. Because this is what we do. When I go from here to here, the operation that I did here is I projected everything on 0. So I applied the projector, and then I renormalized. But here I'm going to work everything proportional to, in order not to bother too much with normalization factors. So here, this is what I do. So now, what we end up with, as you can see here, is a, so I'm going to call this f tilde of s of x. Okay, I can always do that. So I'm going to say that what I obtain here is a state sum over x from 0 to 2m minus 1 of fs of x times x tensor s. Does everybody agree with that? So is this state factorized between the two registers? Right? Is everybody convinced that here it's really a factorized state? This tensor this. So it's no longer entangled between the two registers. And now it means that essentially what remains to be done is feed this state here into the quantum Fourier transform, right? Because this state is the one living on the first register with m qubits. So now I'm going to input this state to the QFT. So the only thing that remains to be done is check whether this f tilde function does have the same periodicity as f. And then I'm done, okay? So let's just check that fs tilde, so fs tilde of s is s f of x. And so in other words, now let me check that f of s of x plus r, well, in fact, it's quite obvious that if I call r the period, then since f is periodic of period r, I get, s, so that's f of s of x. So that's done, okay? So I checked explicitly that if r is a period of f, then it's also a period of f of s. So I'm done. So it means that now the result I'm going to get at the end of my Fourier transform, so if you want the f tilde s hat of k, so the Fourier spectrum corresponding to this is going to be peaked at 1 over r. And so if it's peaked at 1 over r, when I'm going to measure this register, I'm going to get essentially a bit string corresponding to 1 over r. And that's it, I'm done. Of course, there's lots of things I swept under the rug, but I guess Pierre-Alain will tell you more about the dirty details, okay? But the rough idea is that here I constructed a function which is periodic in a period that I want to know, and through a Fourier transform, I can extract this period. Any question on this? And it's very important because it's the only algorithm where we know we have an exponential speedup. So, all right. So if there are no questions here, I'm going to turn to another algorithm that uses Fourier transform a lot, which is phase estimation. And actually, the way I explained Shor's algorithm here doesn't use phase estimation at all. I didn't pronounce the word phase estimation, but there's an alternative way of viewing Shor also as a phase estimation routine. But I'm not going to take this perspective today. So phase estimation, so you remember yesterday we had a small analogy with two Young slits, and we had seen that if I have light here, what I'm going to see on my screen is a cosine. And the corresponding circuit was a Hadamard gate to split the ray in two, then a unitary to dephase it if I have an input vector which is an eigenstate, and then I do a Hadamard gate to interfere, to have interference patterns between the two. And we had seen yesterday that the probability of getting 0 on the qubit was a cosine squared of phi half, where phi is the phase corresponding to the vector. So I had said that u times phi was exponential of I phi, and the goal was to find phi. But we had seen that the number of shots we needed was 1 over epsilon squared, where epsilon is the error that I do on the phase estimation, so that was not super nice to do. So now I want to argue that with all we learned about quantum Fourier transform, we can do better. And the inspiration is also physics inspiration, where instead of 2 slits, we can take n slits. So if I now have n slits, and I put light here, what I observe here as an interference pattern is going to look more like this. And the width of the peak here is proportional to 1 over n. So in other words, if I have more slits here, the width of the peak and therefore the resolution I have on the determination of my phase is much better. And this is essentially what phase estimation does. And we're going to see exactly as here we did it with the quantum circuit, we can do this experiment with the quantum circuit as well. And so it's very easy. I'm just going to perform the same trick as for this circuit here. I'm going to start with, so this is my first slit. It splits. So it splits, so I'm going to put the vector here. So first, I create a dephasing here, 0 plus exponential of 2 I pi, or let's say I pi phi. So this is the dephasing that I create here. And now I want to have a second slit. I mean, actually, there's 2 slits. That's 1 slit. That's 2 slits, right? One Hadamard gate is 2 slits, you remember? You have 2 slits because I have 2 rays here. But now, if I want to have 4 slits, I add a second qubit here. And I'm going also to dephase it, but this time I'm going to dephase it by twice the phase. So in other words, what I get here is 0 plus 2 I phi is 2 I pi times phi. And you see where I'm going, right? Because so remember that the trick here was to say, here I had a dephasing E I phi between those two, but here the idea is the same. Here I have E I phi, and here I'm going to have E 2 I phi, and so on and so forth. That's why I'm having a regular spacing here between the powers that I'm putting here. And so similarly, I can do the third one. So third one is here, u to the 4, and so on and so forth. So that's what I'm doing until the last. So here I have, let's say, m of these qubits. U to the 2m minus 1 here, like that. All right, so this is exactly doing the n-slit experiment. Instead, the big difference is that here, my number of slits here is in fact 2 to the power m. And you can more or less see where I'm getting at. Here I have an exponential number of slits. So I'm going to have an exponential precision. That's it. And so now, in the last part here, now I'm going to do the Fourier transform, because you remember I told you that if I have a transmission t of x, here, what I read on the screen, here is the Fourier transform of t of x. So I need to do my Fourier transform. And this is what we worked a lot for before, QFT of m qubits. And now the claim is that here, if I read the state on the ancilla qubits, I'm going to read the phase. Okay, and so now the goal is to prove that. So now I created a circuit to do a multi-slit experiment. And what we want to see is that it achieves what I claimed it achieves. So let's see. So we're going to work out the actual math. So we start our first state, psi 0, after the Hadamard, the wall of Hadamard gates. So I'm going to call it psi 1, is going to be proportional to sum over, let me call it k, from 0 to 2m minus 1 of k, tensor my vector psi. Okay, and then what I want to do is apply, apply now the controlled unitaries. So for this, I'm going to use a notation which is slightly different here to make it simpler. I'm going to say that this is in fact the state 0 plus 1. So let me spare you the square root of 2. 0 plus 1 cross 0 plus 1 tensor 0 plus 1, so n times tensor psi. So this is my initial state after the wall of Hadamards, and now I want to apply the control unitaries. So let's see if I do the control unitaries to the 2 to the k, for k equals 0 to n minus 1. So let's see what happens. So you see, it's like so it's exactly what I wrote on the board. So 0 plus exponential of 2 of I pi times phi times 1. Then the second one, so that's for the first qubit, tensor. Second qubit is going to be 0 plus exponential of I pi times 2 phi plus 1. And then 0 plus exponential of I pi 4 phi times 1. And so on and so forth until I reach 0 plus exponential of, oops, so that would be, so let me write it here. 0 plus exponential of I pi times, okay, let me think one bit. Why did I put I pi? So the pi is too much, so I don't need pi's, right? Because the phase is defined. Actually, the phase is defined with 2 pi. That's the correct way. 2 pi, 2 pi. So there's a mistake at the top here when I do the definition. In fact, maybe let me. Okay, let me. So on the board, you should read that the definition I choose for the phase is that u times phi is exponential of 2I pi phi times phi. So there's a factor of 2 here that I want to have. And then the last is going to be 2I phi times 2 to the m minus 1 phi. Okay, so we're almost done. So first, do you agree with what I wrote here? So here I applied the control unitaries, and the state that I get is not entangled, right? It's still a product state. And now what I want to do is now focus on the state that I'm going to put in yellow brackets here. So this state here I'm going to call, I don't know, psi 2, for instance. And I'm going to massage it a bit so that it looks nice. So let's see. So this state is essentially a big product, a big tensor product from, let's say, K. So let me call P from 1 to M of sum of Kp from 0 to 1 of exponential of 2I pi times Kp Kp, and then here I have 2 to the p minus 1, if I'm not mistaken. So please help me and check that I wrote it correctly. But so I have a big tensor product on m terms, and then each term is the sum of two components. The Kp accounts for the 0 and also for the 1, and then I have 2I pi Kp to the 2 to the n. So in principle, it should be correct. And now I'm going to do the same trick as yesterday by swapping the tensor products and the sums. So let's see if I can convince you that it works. So I'm going to tell you that I can write it as sum over K1 Kp for all of them in 0, 1. And then I have a tensor product. And the tensor product, in fact, I can absorb it so the product of exponential is going to be an exponential of a sum of P1 to M of Kp 2P minus 1 times K1 Km. Okay. All right. So, and I'm missing one thing. I missed the phase on the way. So the phase, phi, has disappeared. So I need it here. So now, you see, I'm almost done. I can rewrite it in a simpler manner by writing is k from 0 to 2m minus 1 of exponential of 2I pi k times phi times k, where what I call k here is sum over p from 1 to m of kp of 2p minus 1. Okay? And so you see here the convention I use for k is a convention where the most significant bit here is on the right. Okay, so it's a strange convention, which makes me think that in fact here. So remember yesterday. So maybe that's something I should remind you. Yesterday we saw that QFT here. I need to be careful because the circuit I gave you was. I have J as an entry point and K here, the variable. But k here has the most significant bit on the left, and here most significant bit on the right. And we see here that here I'm in the convention most significant bit on the right. So if I put a QFT here, I'm going to be in trouble. So what I should put here in the in my phase estimation is not a QFT, but an inverse QFT. So that means that what I should have written, no, not here. Okay, but you see what I mean here. The QFT on the very top, at the very top here is not QFT, but QFT minus 1 or QFT dagger. Maybe I'm going to correct it. So here this is QFT dagger, and there was 2 I pi, so 4 I pi here, so on and so forth. All right? Okay, so now back. All right, so now let's check what we have. So we have a signal here. So this is the input to the QFT, to the inverse QFT here. And let me call this amplitude here, let me call it x of k, or yeah, x of k, or y of k, to make you think of the y of k in the Fourier transform. And so what is special about y of k? If I define y of k to be exponential of 2 I pi times k times phi, what do you notice about this y of k? About its period in particular. So if I suppose that so if I do 1 over k plus 1 over phi, which I mean, it's a bit strange to do that because here this is not necessarily an integer, but let's do it anyway. Then you can see here that I recover y of k, right? So here it's if 1 over phi is in z, then I can do that. In practice, it's not the case, but so I'm not going to do the full derivation for this point. But you see here that now the amplitudes as an input of my inverse QFT have a period of 1 over phi. So now for the same reasons as before, if I input this signal to the QFT and I now plot the y of j, so the x of j, sorry, so the amplitudes, or even the probabilities p of j after my Fourier transform, I'm going to see here a big peak at 1 over phi. And that's what phase estimation is all about, is that I created in a clever fashion a signal which is periodic in 1 over phi. And sorry, so period is 1 over phi, so what I'm going to read here is directly phi, sorry. So the period is 1 over phi because I designed a clever circuit that produces a signal that has the period 1 over phi, and then as a result, the Fourier spectrum is going to be picked at phi. And that's the way that I'm going to have access to phi. Okay? Well, and something important to realize is that the accuracy I have here is going to be limited by my number of bits on the ancilla register and the accuracy on phi. So essentially phi hat that I'm going to get is going to be like the true phi plus some epsilon, okay, some error. And the epsilon, you can easily see that it's going to be of the order of 1 over 2 to the m, since I have m bits of precision. Okay? So, in other words, what I've shown here in a bit of a sloppy way is that I can get very easily an estimate phi hat of the phase that I'm looking for with an accuracy which is exponential in the number of bits, of my ancilla bits, which is pretty much what I promised in the beginning, because I told you that the precision we get in interferometry experiments is 1 over big N, so 1 over 2 to the m. And now the power of quantum computing is that I can prepare a state which is a superposition of 2 to the m slits, if you want, 2 to the m rays, optical rays, with a price which scales only linearly in the number m of ancilla qubits. So it's very powerful. It's because I have entanglement that I can do that. And now finally, to conclude this part on phase estimation, you can see here that if I do now a cost analysis, so I can do a small cost analysis, and I count the number of gates in my circuit. So you see the circuit top? I have a wall of Hadamard gates. I'm not going to count it. It's 1. I can count it as 1 operation. But then let me count the number of control U2, control U to the 4, and so on and so forth. So essentially, if I want to count how many operations that is, it's essentially 2 power 0 plus 2 power 2 plus 2 power 4 plus 2 power m minus 1. And you can do this geometric series, and you will find that it's 2 to the m operations. Okay? If you want to implement this. And why do I count 2 to the m for? So, and the assumption is that u to the 2 power k costs me 2 to the k. And the reason why I do this cost assumption is that, so this is not always the case that it costs this, but if u turns out to be a time evolution operator, so if u is of the form minus I h t, then you see here that taking a power of 2 to the k is like multiplying the time evolution by 2 to the k. And there's a theorem called no fast-forwarding theorem that tells us that if you want to do a time evolution with a time t, the number of gates in the circuit cannot be lower than proportional to t. Of course, there are exceptions, but this is a generic statement that in general, a time evolution of time t takes you t gates. And so here, if you multiply your time by 2 to the k, you will need 2 to the k gates. So that's why I'm using this cost estimation here. So you see here that the cost here scales exponentially with the number of ancilla qubits. And then, of course, I have to add the quantum Fourier transform, but how much does the quantum Fourier transform cost? It's just m squared. So m squared compared to 2 to the m is nothing, so I'm not going, it's not the dominant contribution. So the final cost of phase estimation essentially is 2 to the m. So in other words, the runtime, so let me call, so the runtime here is 2 to the m, which looks like a lot, but now remember that the precision, the accuracy we get is 1 over 2m. So in the end, what we get is that the runtime scales as 1 over epsilon, where epsilon is the accuracy I get on my phase. And remember, the original claim was that we could beat the 1 over epsilon squared that we got from the Hadamard test. And this is exactly what we do here. So here we have 1 over epsilon. And in fact, this cannot be beaten. You cannot do better than this. This is called the Heisenberg limit. And this is why we do quantum mechanics, essentially, is to go from a scaling at 1 over epsilon squared, which is central limit theorem, essentially. And you go to this, which is the quantum way of measuring an energy. So this is what we achieve with quantum phase estimation. And in the hands-on this afternoon, we'll actually implement this phase estimation and do it for an actual molecule. So we'll take a quantum chemistry example and compute the energy of a molecule using this phase estimation algorithm. Okay? Any question to this up until this point? No? Let me. So now we're going to slowly turn to more practical matters. And so one very short thing I want to say before turning to very practical matters is just an implementation detail, is that so far I told you we have a unitary U, and let's work with this unitary U and do the quantum circuit with the control U operation. Now the question is, in practice, you have to implement this U. And so one way that Yassin mentioned yesterday already to implement U, so suppose you're interested in a Hamiltonian H, and you want to find the eigenvectors of this Hamiltonian, then a clever way of using phase estimation to solve this problem is to say, oh, let's construct u equals exponent of minus IHT. And then I know that u times phi is going to be exponential of minus IET times psi. So, and you remember that what we called this is, we said this is u. We can redefine the phase in this way. So in other words, if I use phase estimation to get phi, then I can get the energy by writing that 2 pi phi equals minus ET. So I can get the energy as 2 pi phi divided by T minus. Okay, so one way to find the eigenvalue of a Hamiltonian using phase estimation is to say, I start with an eigenvector, which is a strong assumption. I feed it to phase estimation, I get a phase phi out, and I recompute the energy in this way. Okay, so this is one way to do it. But having said that, I've swept under the rug the fact that I need to find a quantum circuit to do this U here. And so Yassine already mentioned it, so I'm not going to spend too much time on it, but the simplest way to do so is to say, okay, first, I need to decompose my Hermitian operator H as a sum of product of Pauli matrices like this, and this can always be done because Pauli matrices form a basis of my Hilbert space. So here this is a product. So for instance, it could be identity times sigma x, which I'm going to call x, times y. For instance, one of the PIs could look like that. And also I have to warn you that M here needs to be quite small. In other words, I hope that I'm in a case where M is polynomial in the number of qubits of my Hilbert space. Because if I have an exponential number, then it's going to be, just representing it on my classical computer is going to be too large. So I need to be in a case where this is the case. But it turns out that for chemistry, for instance, or for physical systems, it's always the case that M is polynomial in N. And once I've done that, what I like to do is an exponential of a sum. And of course, exponential of a sum is not something that I can do in principle. I mean, I cannot turn it into a product of exponential unless I slice it into pieces. So I'm going to divide and multiply by NT. And now I'm going to do an approximation that this is in fact product from K to 1 to NT of exponential of minus I, so of product of I from 1 to M of exponential of minus I lambda I pi T divided by NT. So here I did an approximation. I essentially turned this exponential of a sum into a product of exponentials. But now, okay, why do I do at such great length to explain you that? Is that this here is of the form exponential of minus I theta I, theta I divided by 2 times pi, where theta I here is defined as 2 times lambda I times t divided by nt. Okay, you agree with that? So now I've decomposed my time evolution into a product of terms which look like that. And my claim here is that this is an exponential of a Pauli term is easy to represent as a quantum circuit. I can take one example, maybe two examples. Let's take the example of, let's say, what about pi equals z? Then, so let me give a name to this guy. So this is r of pi of theta I. So pi z corresponds to rz of theta. And rz of theta, you know already, it's a rotation along the z-axis. Now, a more interesting case would be pi equals zz, like that. So this is what I can call rzz of theta. And in fact, it's quite easy to show that there's a simple circuit to do that, which looks like that. So you do control naught, then you do RZ rotation of theta, and then you do another control knot. And this will do the trick. It's easy you can just check that the two matrices corresponding to this one, and you already know that this one we saw yesterday, that it's cosine theta half identity minus I sine theta half ZZ. So you can check that if you build a matrix corresponding to this and the matrix corresponding to that, to the right-hand side, you'll find the same operation. And in fact, I can carry out the same thing for R of Z, 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 Z. And by induction, I can show that this will correspond to a wall of Hadamard gates, of C0 gates. So I have some dots here. But essentially, I do a wall of like that. And on the last qubit, I'm going to put my RZ theta rotation. Okay, so it's very easy to do an exponential of a Pauli product with only Z operators. And now what happens if I have X and Y? Then X and Y, if you remember the block sphere picture, is just a rotation by pi half of the axis. So I just need to put rotations of pi half on the right axis to turn the Zs into X's. So my claim essentially is that this is an easy term because I can represent it with a quantum circuit. So now in principle, you should be convinced that to represent the time evolution operator U, if I want to compute the eigenvalue of an operator, I can do it with this type of circuits. And this is called trotterization, as Hassin told you yesterday. So this is called trotterization. And in the hands-on this afternoon, we'll do trotterization to compute the energy of a molecule. And you'll be able also to measure the error that you're doing, because here it's an approximation, and you can also estimate what is the error you're doing as a function of the number of slices NT that you're doing. So you can imagine that the larger NT, the better, because you're getting rid of commutators. But that's it. All right, yes?
When you do the phase estimation on the left, the phi depends on T?
Yes. So the question is, when I do the phase estimation here, the phi depends on T. Yes, it does. And in fact, that's something I didn't really explain, but we would like the phase here to be between 0 and 1. And in fact, if I want the phase to be between 0 and 1, the energy here is something I do not control. That's what I'm looking for. But I need to make T. So for instance, if I have a very large energy, then I should have a very small T. Right? So I need to adjust T so that my phase in the end is going to be between 0 and 1. But in practice, you'll tell me, yeah, but I don't know E, I don't know the energy, so how do I choose T? So for phase estimation, you need to have an estimate of where your energy should be, so what is the range? So you need to have a lower bound and an upper bound of the energy in order to fix T. And in fact, you have even to do better, because if you have negative phases, you'll be in trouble too. So what you need to do is shift all the energies by a constant shift to make them all negative, and then fix T to all make them within a given range so that you fall between 0 and 1. So that means that you need to have an estimate of where your result is, but that's usually the case. You have a classical method that tells you, okay, at most I can be E max, and at least I have E min for my energy. Then you shift your Hamiltonian. You pick a time so that in the end you're guaranteed that your result is going to fall between 0 and 1. And physically it makes sense, because if you're looking for very small energies, you need large times. And this is what we have in mind in spectroscopy, for instance. If you probe a system and you want to learn about its low energy properties, you have to wait for a long time. You need to probe the system for a long time. And this is what we see here in a way, in an algorithmic way.
So in practice, you obtain the energy at the end of the simulation. At time big T, you can estimate phi and you get E.
Yes. So I have a first rough estimate of the energy range that helps me pick small t. Then I do my phase estimation, which depends on t. I get phi, and then I do phi divided by t, and I get the actual energy. And so, but we'll do it this afternoon, and this afternoon we'll put the right shifts. And in the notebook this afternoon, I put the precise explanation of how we do the shift and the rescaling. But it's actually one of the big subtle points that debugging this afternoon's notebook took me quite a while to figure out. So it's a good point. Yes?
What kind of algorithm can you write
Yeah, so it's the question is, what kind of Hamiltonian can you put in this form? So what we see this afternoon is that for systems of fermions or bosons that comes from the physics world, let's say, in a second quantized language, which is it's a discretization of the problem, then you can put it in this way, and most importantly, with m polynomial in the size of the system. In fact, any Hamiltonian can be written in this way because H is a Hermitian operator living in a Hilbert space with dimension n. So if I take m to be 2 to the power n, then any Hermitian operator can be decomposed on this basis. But the question, your question is, if I rephrase it, is in which cases do I have a small number of terms? In physics, we have, if we use a second quantized notation, but for instance, in math, suppose your operator here is an operator like a differential operator, Laplacian operator, or something that you have in a differential equation. Then it could be that you have an exponential number of terms. And this is something that will be a problem because, as you can see here, there's a product over m. So that your number of gates is proportional to m. So if m is too large, then you're dead. Yes. Well, so here, for instance, in the molecule we'll see this afternoon, we don't really do an approximation. Within the basis set that we're going to choose for the molecule, we don't do an approximation. Of course, in practice, it's still a discretization, so yes, we're doing an approximation, but it's more or less under control. But yes, at some point, you could also do an approximation of your Laplacian operator and truncate it to m, which is reasonable, and then do another approximation by doing the trotterization. Yes. And so what Agnieszka showed yesterday could be seen as a more clever way to do this. So there are other ways to do this time evolution, which use the block encoding that Agnieszka showed yesterday. So in fact, you can achieve better approximations than what I just showed you, but it's more involved, and that's why Agnieszka's lecture is advanced quantum computing. This is just basic quantum computing. Okay. Yes?
You said that you can write a PI with RZ or ZZ, but is it easy to write RX, Y, Z, XX?
Yes. And the reason is that... Oh, yeah, so the question is... yeah. So here I handle the case where I have only Z operators, but what happens when you have X and Y? So when you have X and Y, you need to look at the block sphere. So the block sphere is this sphere here with X, Y, and Z. And now, let's say you want to handle a case where you have X. Now I need to convince you that if I want to deal with X, I can rotate the X-axis. So I can basically apply unitary operations left and right of X to get back to Z. And the block sphere is a nice way of seeing what we have to do. So you see here, if I want to rotate X to Z, I need to do a Y rotation. And the Y rotation has to be of angle minus pi half, if I do in the right order. So now in principle, I have to do R and here R dagger of Y minus pi half, minus pi half. So my claim is that if you do that, first my claim is that it works based on this geometric argument, but you can check yourself that if you do the math, it works. And once you've done that, then essentially, for instance, if you have an exponential of I theta minus theta times Y times X, I can rewrite it as R y minus pi half times exponential of minus I theta half z times r y dagger minus pi half. Okay? And so the reason why I can go from this to that is the trick with what the exponential means. So you remember exponential is cosine of identity minus sine of x. So if I sandwich this expression with this ry, I get this. So essentially what I'm telling you is that if I want to do, so here it's a trivial example because I have only 2 qubits. I have only 1 qubit, so I could have just done the rotation, the rx rotation. But let me take an example where I have here times z, for instance. So this is a 2 qubit here. So x times z. Then I just need to do, and of course I need to say that I have ry on the first qubit and identity on the next. And here identity on the next qubit. So in other words, to implement a rotation xz, what I need is a circuit that looks like that. So first I do ry dagger minus pi half on the first qubit. The second one I do nothing. Then I do control. Then I do rz of theta. And then I do my C0 gates left. Then I do my last ry of minus pi half. So that should answer your question, that now I can do the rotation here. In this case, it's probably not the most clever way. I can probably do something more clever, but at least this works. And the reason why I put the R dagger first is that you have to read from the quantum circuit from right to left. All right? Okay. Any other questions? So here we will essentially implement this afternoon so that you know exactly how to do it for a molecule. So now I want to say a few words about what we have today, because essentially you can forget about all I said for today's computers. So today, nobody, at least in their right mind, does any of this on a quantum computer. Why? Because the number of gates you have is too large. All the algorithms that we've seen, the moment you have a quantum Fourier transform, you can forget about it. So now I'm going to spend the last 15, 20 minutes to tell you a bit about what we do today in quantum computers. And it's very simple because since they're pretty limited, we do quite simple stuff. And maybe something I want to explain is why we are so limited in the number of gates we want to do. And so yesterday, Maziar introduced you to the formalism of density matrices, which is the way you describe a noisy quantum state. So I'm not going to spend too much time, but just to remind you, so far we've said that if we do a time evolution in quantum mechanics, we essentially multiply the wave vector by a unitary matrix. It turns out that if you are dealing with a quantum computer with noise, you just change the picture by describing the state with a density matrix object on which you apply a map, which is a linear map, which we usually call epsilon, which is linear, which is trace preserving. Why? Because you want this object to have a trace of 1. In the same way you want to have your wave vectors to be of norm 1, you want to have this object to be of trace 1. It's really the same idea. And another property of this map is that it's completely positive. And this has to do with the fact that this row, this object here, so needs to have trace 1, but it also needs to be a positive definite matrix. And the mathematical reason is that it's like a statistical mixture. It represents a statistical mixture of states. So I don't really want to go into the formalism, but so you'll have to believe me on this, that we can replace gates by, instead of unitary matrices, we replace them with linear applications on this object. And when we're talking about noise, and just one important point is that you can go from one formalism to the other very simply by saying that if you have no noise, then rho can be written as the ket psi times the bra psi. So this is the noiseless case. And in this case, you can see here that if you do a gate, here a gate is like u psi. And if I do the bra equivalent, it's going to be u dagger on the left. And here, since this is rho, you see here that a noiseless gate is u rho u dagger. That's what a noiseless gate does on this object. Right, so this is what I'm going to call a noiseless gate. And so a very simple model of decoherence. So yesterday, Mazia introduced you a very general notation for a noisy gate, which I can give you so that you remember what Mazia told you yesterday. So the most general way of representing a noisy gate would be to generalize this u rho u by e k rho e k and then sum. And these operators here are called cross operators. So essentially, if you want to describe completely a noisy quantum computation, you just give me for each gate what are the cross operators. And so the size of these objects are different. So here we have 2 to the n for psi. Here it's a 2 to the n times 2 to the n matrix. And the cross operators are also 2 to the n times 2 to the n matrices. Okay? And this is the complete description. So you can really do, within some assumptions, but it's pretty general that you can describe gates, noisy gates with this model. And so for instance, now let's say you want to do a Hadamard gate. And I'm telling you, no, this is a noisy gate. I have two main ways to explain. Either I say, in fact, it's a noisy Hadamard gate. For instance, let me call it H tilde. And you're going to give me the cross operators. And that's it. And you can get these cross operators by doing tomography of your quantum computer. Now, if you're more of a theorist or you don't have access to the full tomography of the gate, you can say, essentially, this noisy gate is a perfect gate followed by some noise process that I can call a noisy gate N. This is something that we like to do. And so therefore, what we say is that we first do a perfect Hadamard gate followed by some noise process. And one noise process that is used a lot, especially by theoreticians because it's easy to make computations, is called the depolarizing noise. And the channel corresponding to depolarizing noise, which I'm going to call epsilon n of rho, is very simple, and that's why I want to mention it today, is 1 minus p times rho plus p times identity over 2 to the power n. So let me explain. What it means is that if you have a noise of the depolarizing type, let me write it here. So this is depolarizing noise. One minus p% of the time you do nothing to your state, and p% of the time you turn it into an identity matrix. And it turns out that the matrix, the density matrix corresponding to identity is essentially the state where you have no information at all. So essentially, this depolarizing channel erases all the information with probability p. And so why I want to mention it is that I would like to motivate the fact that if you have a succession of a big NG of these depolarizing channels. So essentially, if you apply this map NG times, NG is the number of gates, it's easy to show that ENG times, so power NG, is going to be 1 minus P power NG times rho plus essentially the rest, so 1 minus P power NG times e to the n. So here I just did by recursion also here, so you can show this easily. So if you do a lot of these noise channels, you'll see such a result. And the reason why I want to emphasize this is that a very interesting measure that we use all the time in quantum computing is the fidelity of a state with respect to another. And in our case, what we want is to check the fidelity of the state I would have gotten in the absence of noise and the state with noise. So in the absence of noise, I would have gotten a state psi. And the fidelity is actually, so let me call it rho at the end. So the fidelity is defined like this. So I do a sandwich of the perfect state I would have gotten at the end without noise, sandwiching the actual state I get after my noise process. And rho end in my case is this, right? Rho end is this. So now let's see. And of course you can check that if I had no error, so if rho end were psi psi, then of course in this case you get that f equals 1, right? If rho end is the same as the beginning. But now what happens if you apply this formula to the expression above? You see that I put my psi, I sandwich, then so this here, the initial rho here is psi psi, it's the initial state. So this gives me 1, so I've got 1 minus p power ng. That's the first contribution. And the second contribution is going to be plus 1 minus p power ng. And then if we look at this here, it's just contribution 1 also divided by 2 to the n. So here I want to do this computation because here I have a number which is small divided by 2 to the n. I mean, even if it's not small, it's divided by 2 to the n, so with a number of qubits which is quite large, which is even not so large, I can remove this term. So essentially what is important to remember from this is that, and this is a very important law. Okay, I'm going to put an approximate sign here because I removed some terms, but is that the final fidelity that I get if I do ng noisy gates is essentially 1 minus p times ng, which I can rewrite in another way. If I do an inverse Taylor expansion, it's e minus p power ng, okay? So in other words, the fidelity of the state, so the quality of my final state decays exponentially with the number of gates in my program. So, and that's why yesterday I told you at the very end of the lecture that if I want to have a reasonable fidelity, I want to have ng of the order of 1 over p, where p is the probability of mistake, of error per gate. So that's why if you want to know how many gates you can run on a quantum computer, you just have to ask the hardware maker what is your p, and then you can tell what is number of gates you can run. And so on today's hardware, let's say not the best ones, but reasonable ones, you can get 0, and yesterday I made a mistake, this is 10 to the minus 3, not 10 to the minus 4. So that means that the number of gates you can do is of the order of 1,000. And right, if you do ng times p equals 1, you already get a quite big reduction, right? So 1,000 is probably too much compared to what you can actually do. But that's a very important law to have in mind. And if you look at Google's experiment, supremacy experiment, and you use this formula and you use how many gates did they have and what were the fidelities, you get a fidelity of 0.2%. So even in the 2019 paper of Google where they said we have quantum supremacy, the fidelity of the state was 0.2%. So these are very small numbers even on the best machines, because this is an exponential, okay? Any question on this? Yes?
Is that the same P for all the gates?
No. So the P is different for the gates. Essentially for 1 qubit gates, it's 10 times lower than for 2 qubit gates. Essentially, that's the order of magnitude. So, and you could actually have a better formula where you do like for instance, you could turn it into 1 minus P1 times the number of 1 qubit gates times 1 minus P2 times the number of 2 qubit gates, so you can make it more precise. Okay? And here, so there's a lot of assumptions in all this computation. I deliberately chose a depolarizing noise, and it could be that the computer you have is not depolarizing noise. But in fact, in practice, it does work quite well. So this rough computation works quite well to describe the fidelity of the final state. Okay, so now in the last 5 minutes, so yesterday, Yacine told you about the variational quantum eigensolver. So, which is essentially the only algorithm that people do on today's machines. And I'm just going to tell you 2 words about it before I conclude. So in this variational quantum eigensolver, which is going to be also an algorithm you're going to implement this afternoon, because it's much easier to implement, what you do is that you forget about everything we said before. And you use an old method that is used a lot in math and physics, which is called the variational method or variational principle. You create a wave function that depends on a parameter or several parameters theta. And then you try to minimize over theta the value of psi theta h, where h is a Hamiltonian that you want to minimize. So it could be a combinatorial optimization problem like yesterday in QAOA algorithm. It can be quantum chemistry that like we will do this afternoon, in which case you already have this decomposition. And by doing so, you hope that if your variational space is expressive enough, this should be close to, actually you're guaranteed that it's going to be larger or equal than the actual ground state energy of your system. And so the idea of this VQE, variational quantum eigensolver, is to design a circuit here which is clever enough that you can reach an energy which is close enough to the ground state energy, but also that is short enough to beat decoherence. So you want it to be very short, because if you don't, then you're going to be killed by the arguments that we had just before. Okay? So you need to design circuits which are very short and nevertheless smart enough that you will get a good enough energy. And this afternoon we'll play with several circuits and see, okay, how they work and so on and so forth. Now, one remark I want to do is how, in practice, we compute this. Because given what we saw this morning, what we just saw with phase estimation, it would be tempting to say, let's take this state here that we optimize, and let's feed it into phase estimation. It would work if you had a perfect quantum computer, and if the overlap with an eigenset were good enough. But in practice, it's not always the case. So first you have decoherence, so you don't do phase estimation, and it could be that the overlap here is not large enough. So that's why we don't do it, and the way that people compute these energies is essentially to use the formula here for H. They do a sum of the lambda I psi theta pi psi theta. And then what they do is that they compute individual terms. Here they compute individually the expectation value of this term at a cost, epsilon, I mean a statistical error, which is always 1 over square root of ns, where ns is a number of shots. Because as always, when you do a measurement on a quantum computer, you need to pay the central limit theorem, because you do an average, you do a classical average. So the cost of VQE also scales, so VQE runtime also scales as 1 over epsilon squared. So it's not, you're not using the full power of quantum computing, but that's because if you wanted to use the full power of quantum computing, you would need phase estimation. This is too long for what we have today. And I think I'm going to stop here to have enough time for questions.
While you think about your questions, look at your emails. You received an email by Romeo. So there are 2 people from the Romeo platform here who will let you try it if you are interested tomorrow evening during the slot, the discussion slot. So you have to answer their email if you want to participate.
And so maybe to advertise what Romeo is. So Romeo is a platform where you can do big scale quantum emulations of quantum computer. And the language to program on this Romeo platform is MyQLM. So what you will do in this afternoon in the hands-on will be helpful then to actually do runs on this big platform, because this afternoon we'll run the hands-on on your laptop. So you can reach probably 20, 25 qubits. But if you go on Romeo, you can reach, I don't know how many qubits you can do.
Depends on the number of participants.
So
Well, I don't know exactly, but depends on the number of gates you're simulating and depends on the number of participants.
But if you have one participant that wants to run a very big circuit?
100, I think.
Okay. Well, 100, okay.
Depends on your circuit.
Yeah. Yes.
So maybe if we are too many to want to participate, we can be joined by two, make teams of two. So that everybody gets a chance to run some. We can do binomes for tomorrow's.
So maybe if we can save some space on the machine, so you can maybe group by two, and so work together. So that would be an occasion to discover your neighbor.
And I think the participants to the hackathon already have an account on Romeo. You have the names already. Yeah. So the mail you received is really for the participant for only the school, this week's school, if you want to have a chance to try the Romeo platform.
And maybe also as a further motivation, you see here, if you want to, you have a very nice optimization algorithm and you make your noiseless simulation and you say, oh, my circuit is perfect, I have very good results. And you want to actually know whether it's going to work on a noisy quantum computer of today. Then, because we have this density matrix formalism, we can simulate the effect of noise. The issue is that you see the size of rho here is 2 to the n times 2 to the n. So it's a much bigger object than the wave function. So on our laptop, you will be able, and actually this afternoon we're going to do a small noisy simulation, but very small because it's a huge object. But if you want to really simulate your QA/OA algorithm with noise in realistic conditions, you need to have access to bigger emulators like the ones on Romeo. So it's quite nice that you have the opportunity to access a very big machine like that. Yes?
So one online, do you think you have any references on quantum noise?
Yeah, so the question is, do I have any references on quantum noise? So there are other standard textbooks like Nielsen and Chuang and Preskey's lecture notes. You can look on the slide that Agnieszka gave yesterday. There's a lot of very good references. Otherwise, I will also provide some lecture notes corresponding to the 2 lectures I gave yesterday and today, where I go in a bit more detail about what density matrices are, what these cross operators are, and so on and so forth. So I will also provide some lecture notes on this topic.
Okay, any more questions on this morning class? If not, we go to the coffee and we come back in 20 minutes.